Hi everyone. Thanks for joining us today. My name is Cheryl. I'm a partner here at Dragonfly. Today we have the privilege of having Ben with us from Jensen. Ben is obviously co-founder of Jensen, where it's one of the leading players in the AI compute space. Ben, would you like to kind of give us a rundown of Jensen and what you guys do?
Absolutely. Thanks, Cheryl, and hey, everyone. Yeah, as Cheryl mentioned, I'm the co-founder of Jensen. Jensen is a machine learning compute protocol. So we're a layer one protocol for connecting machine learning capable compute devices, any kind of machine learning capable compute device in the world, and then providing all of those devices as a resource to anyone who wants to train a machine learning model. So the idea is, as a machine learning engineer or researcher, instead of using one of the kind of centralized cloud providers and accessing a set of GPUs in a data center that they run, you can access any GPU or TPU or CPU in the world, and kind of any amount of those devices, and just pay the owner of the devices. So it's an infrastructure where it's fully open source. You just run the software and you're part of this huge cluster. And then on the demand side, when you need to access a cluster, you've essentially got an order book or kind of like an auction list where you can just access any number of those devices to train your model. And it takes away the kind of functional size limits that you can access. Right now, if you try and get access to GPUs through AWS or Google Cloud, you'll hit quota limits quite quickly. And you'll also see pretty enormous prices, to be honest, because there's a squeeze on the machine learning compute in the market right now. This software kind of removes that limitation. It replaces a lot of the expensive portions of running a data center and offering machine learning compute. Those expensive portions are typically in the human world, things like legal contracts, customer service, account management, etc. It replaces all of that with code. So the idea is that you can send your task across, you can get the results back, you can know that it's been done correctly, and you can trigger payment all programmatically. There doesn't need to be a human involved in that whatsoever. That solves a lot of kind of prior kind of backwards looking supply constraints and price issues and scale issues within that market. But in a forwards looking way, it also allows machines to interact with this infrastructure. So it gives AI models themselves access to the compute resources they need to train themselves rather than having to kind of go via a human. Gets a little bit kind of visiony and future looking when you think about it like that, but that's a lot of the way that we think about the Jensen infrastructure and the kind of future of machine learning. It'll be highly automated, and it'll be lots of kind of models accessing resources themselves rather than needing humans to go out and get a legal contract with a company and kind of sue them if it goes wrong and things like that.
Awesome. Yeah, I feel like today it's pretty clear that NVIDIA is having a pretty tight short chip supply. A lot of AI projects. I mean, obviously with the boom of Gen AI, there are a lot of AI projects nowadays that are starting up. Probably comfort the 8 to 10 mil bill that AWS, Google has been asking for. Either that or frankly, there isn't enough capacity in the centralized providers, like you said. So very glad that there are players out there like you guys, as well as a few other guys like Akash, Render, Ionet, the list kind of goes on in the space. So I guess one is the pitch that there's been scarcity in space. Two is that a lot of these centralized players offer higher pricing. Can you sort of kind of walk us through what are the differences between Jensen and a lot of your other peers in the space as well that we mentioned?
Sure, yeah. I guess probably the clearest way of thinking about the differences between Jensen and everybody else is that we focus very low level on creating that infrastructure that is programmatically accessible. So when we think about Jensen, we think about the kind of early internet and the way that spread, the way that it was originally created, and it's built on top of a set of open source protocols. So in the protocol wars of kind of the late 20th century, there were lots of these competing standards, and out of those standards came the TCP/IP stack, basically, which is a set of open source standards for interacting between devices. Those open source standards allowed us to build the internet infrastructure that we have now because they had a standardized way of interacting between every device in the world. So all of our devices now kind of talk over the internet protocol stack. We think machine learning is a very big change to specifically the way humans access data and interface with the kind of shared knowledge base that we have as the internet. But for that to spread and be as kind of prevalent and as powerful as we'd like it to be, we need a new set of standards for the interactions. And crucially, the bottleneck isn't communication anymore. That's what it was for the kind of start of the internet. Now it's compute, because those models and the ways we interact with these new data structures, these embedding spaces, are via machine learning models themselves. And those machine learning models need access to compute in order to run. And there's lots of kind of people building these specific ways of interacting with compute. You go through them, like you access their compute specifically, and they kind of get you as a customer, and it's hard for you to leave. What we'd like to develop is a completely open layer, which is very similar to the TCP/IP stack, but allows everybody to access compute in the same way, in that standardized way across the planet. So it becomes this huge efficiency mechanism over all of the compute devices we have. There's one big crucial thing you have to solve there, though, which is compute resources cost money. Like there's a base cost to accessing them. There is a base cost to the communication protocols as well, but that base cost is it's a lot smaller, and it gets kind of eaten by telecoms companies. The way it developed went reasonably well for the world. We managed to keep it open. Telecoms companies do have a bit of a kind of hold on it, but it didn't create any like terrible monopolies or anything like that. When we were developing the protocols for compute this time around, we want to learn from what happened last time around. We don't necessarily want to hope that emerges in the right way and that the companies don't end up monopolistic. We'd like to bake that into the low-level protocol. So you get resource accounting at the lowest level, as if TCP/IP had resource accounting for bandwidth and latency as the kind of resources it's using. The same for compute. We want resource accounting for the ops that are being performed. And if that's baked into that open source protocol, you know when you're sending your operation to another compute device, you're actually kind of paying for exactly what's happened there. You're not paying some kind of huge hidden margin for some reason that somebody's trying to kind of extract from you. So we think very much in that kind of protocol design way. I think a lot of the other companies you mentioned think a lot closer to how can we emulate what we have in the centralized world, but make it cheaper or make it higher scale. And that is useful, but to us, that's the sort of 10-20% increase or decrease in terms of cost on what we currently have now. It's an improvement, but it's not a huge change. We're looking for that huge change. We want to develop the new standard and usher in essentially the next technical revolution, where the internet was the last one. We think the next one is humans interacting via models with the huge shared knowledge base, which currently is the internet, and in the future will be these model embedding spaces.
Gotcha. Very cool. Yeah, would love to delve a little bit more into the resource computing in terms of not just providing the bare metal, but also having this software layer that really enables developers for much better experience. Before that, I did want to touch on another pretty big differentiation in my view, at least, on what Jensen really does. So Jensen allows for on-chain training, unlike a lot of the other players out there that are probably a lot more focused on inference. And it's obviously quite a big difference given that with inference, you can probably just use one node, whereas for training, you really have this parallelization of compute, which is a lot more compute intensive, a lot more technical. I was hoping you could kind of walk through that because that is quite a big differentiation with you and the other players as well.
Yeah, absolutely. We view inference as, in many ways, an easier problem. That, like you said, it can typically be run on a single node. You can heavily quantize models so that they fit on smaller devices. You can use sparse models. You can do a lot of tricks on top of a model to make it effective for inference. You can also just kind of decrease the performance of the model, squash the model down, and still get acceptable inference performance. What we see in the inference space, though, is much fewer constraints than you get in the training space. So because people can do that, the goal of most organizations that are doing heavy inference is to get that model as close to the user as possible. Their kind of internal drive is to get the model running on the user's device, ideally. And outside, kind of going away from the user's device, we expect to have this sort of like granular caching layer sort of step going away from the user. So there's a very small kind of quantized model running on the user's device, which will be the initial inference kind of answer. And then slightly further away in a typical kind of CDN style caching layer, maybe you'll have a bigger model. Further away again, you've got a bigger model. But it starts to replicate the kind of internet caching layers in our view. That's not necessarily a great problem for decentralized technology to solve. If you're building a network that is designed to be a CDN in that way, it's designed to kind of run infrastructure as close to the user as possible, you're gaming latency in that way. And the best way to do that is to have massive coverage. As a decentralized network, if your goal is to have massive coverage and if your value is linked to having massive coverage, you're subject to Metcalfe's law, which is essentially the size of your network is kind of or correlates with the value of your network, which means you have to bootstrap incredibly heavily in order to actually have value as a network. We've seen this in the kind of previous deep in wave, like Helium had this exact problem where the kind of value of that network was based on its coverage, which means you have to heavily bootstrap supply and know that your demand side will take over because you can only bootstrap for so long. That's a really hard problem to solve as a decentralized network. And ultimately, we view the kind of inference problem as just moving more and more and more to the edge and getting compressed more and more so that users will be running these devices. Training, on the other hand, is heavily compute constrained rather than latency constrained. And compute constrained problems are much nicer. You've got these asynchronous tasks where I need to do really heavy compute, but I don't necessarily mind if it takes 30% longer because I'm setting it running and then I'm kind of doing something else while I wait for that thing to finish. That's perfect for a decentralized network because they're not great at latency, but they are great at offsetting like a core resource cost like that. So that's where we focus. They're also great for very large problems where you can amass huge numbers of devices, but like I said before, you've got that kind of like asynchronicity, redundancy. You're not too fussed about that. So it's a much nicer problem to us. Inference will happen in our view in a decentralized way, but it's less clear value proposition and it's probably a longer term value proposition and a bit smaller in our view. Yeah. There's also the piece that we kind of view the distinction between training and inference as a bit of a temporal kind of blip. It's a little bit like if you look at the early internet when you had originally this kind of client-server relationship where the server would create this information that would be read by the user because the creation was very difficult and it was more expensive, and the user would just be kind of visiting the website, getting information and leaving. That was a short period of time until we moved to the kind of content generation by the user, constant back and forth. The client server model sort of kind of blurred into more of a peer-to-peer model where when we interact with websites now, we're also updating records all the time. We think the same thing is going to happen in the machine learning space, where right now it's very expensive to update the model. So the user typically doesn't update the model. They just read from the model. Maybe they do some like RAG or a little bit of RLHF to update the model, but not very much. We think as the compute cost comes down and the ease of updating the model increases, we'll move much more towards that continual training paradigm where when you and I are interacting with a machine learning model, we're not just running inference queries. We're not just reading from the model's embedding space. We're also constantly updating it as well. So Jensen's view is when the model weights are being updated, we want to be the protocol that kind of runs that transaction. When they're being read, somebody else will be doing that because read is very different from kind of update or create in the original internet parlance.
Got it. Got it. Okay. Okay. And the other pretty big differentiation that I thought was pretty interesting was that you guys focus a lot on verification as well, i.e. focusing on in a very decentralized manner. Is the person actually using the model that they actually claim that they would be using? Yeah, how do you guys think about that?
Yeah, good question. That comes down to that focus that I mentioned before of being that really low level protocol where we want to sit just above the electricity. And then every interaction that people have with machine learning capable compute can go via this protocol. But most people will forget and probably not even know that they're doing that. Same as most users of the internet don't think, oh, hey, I just interacted over TCP/IP. Like they don't need to know about that. They're interacting with some kind of higher level application, and under the hood it's going through this kind of standardized protocol. Same for us, but for that protocol to exist and to operate without humans in the loop, it has to have a trust portion built in, and that trust portion has to verify that the transactions actually happened, the operations that were requested have actually been performed. Right now, that same process happens every time you use a kind of outsourced service provider to do machine learning training or even inference, but the trust is established through these kind of human world mechanisms that we don't think about the cost of those, but they are incredibly costly. If you add up all the kind of resources required to establish those, like the legal contracts themselves, the kind of time from a person required to be the account manager, establish that contract with the SLAs, etc., the court system that exists to arbitrate if those contracts are breached, all of that infrastructure has an enormous cost, and it couldn't execute in the protocol situation because it takes way too long to execute and it's also way too costly. with crypto technologies and with blockchain, we can replace huge portions of that with code now. And Jensen's goal is to replace the entire stack for machine learning computation specifically with code so that they can instantaneously execute. Therefore, you can actually have a protocol rather than having to have some kind of like human world sort of wrapper or something where at some point somebody has to step in and have to arbitrate or has to do KYC or something like that. So that's why we focus on verification, because you can't have the protocol we described without verification. If you just wanted to build an AWS style interface that benefits from kind of the scale of like decentralized access to compute, you could do that right now, and you could establish the trust with a KYC process behind the scenes, or you could just kind of run it without trust and say, okay, maybe some people will be dishonest, but like generally it'll be decent. That works up to a certain scale, but it doesn't go any further than that. And our goal is to get maximum coverage, be on every single device. The only way to do that is to have verification built into the tech and the code, because it eliminates all those pieces that will grow. If you have value locked in this system, there will be people who want to extract that value, and they will be able to if you don't have a verification system.
Right. And I guess on chain, there are a few ways to do different types of verification. Some are obviously doing more crypto economic CE ways of security. Some are doing, foolproof ZK. Some are doing optimistic. Obviously, there are different kind of flavors with different kinds of trade-offs between security. How about you guys kind of thinking about tackling that?
Yeah, we've been doing this for a long time, so we're pretty knowledgeable about the whole space. Our stance is there's no one silver bullet technology here. It has to be a combination of technologies. Ultimately, if you could have a cryptographic proof system, that would be the absolutely most secure way of doing this. So imagine you have a zero knowledge proof of a full machine learning training task, which can be created by the person doing the training, can be submitted to the chain, and that proof can be checked. It could be non-interactive. It could be instantly checked if you wrap it in Fiat Shamir, or it could be an interactive proof, but it would be very lightweight to check, and it would be that kind of instantaneous proof of the whole computation. That's the kind of gold standard, but realistically, it's ridiculously expensive to achieve that, and it will be for quite a long time. The next kind of potential verification system you've got is like a probabilistic, almost like optimistic kind of roll-up style check where you can rerun portions of the computation as long as the computation is deterministic, and you can use kind of probabilities to know that if you've done 10% of the checks in a random way, or 20% or however much you need to do, that the whole computation was probably done correctly up to some percentage guarantee. If you wrap that in a game theoretic approach with incentive mechanisms, then you can have this kind of optimistic style checking where you can be reasonably certain, and you can tweak it. You could go 80% with very minimal checks, or you could go up to 99.99 whatever percent with more checks, that computation's being done correctly. Ultimately, the Jensen solution is a combination of all three of those things. So we have our own interactive proof system, which is a cryptographic proof system for a portion of the checks. Because it's expensive, we only use it very deliberately and in very specific areas, but it provides the kind of very strong guarantees that you want from a cryptographic system. And then at the same time, we have this probabilistic system where we're auditing, guided by those game theoretic incentives as well. So you can trade all of those off based on the resource costs of them and the time costs and things like that, to get the most robust system at the lowest cost that's maximally efficient for the user. You can also hand some of the decision for that to the user. So in some use cases, somebody will be very keen to have perfect guarantees that this has been done correctly. In other situations, imagine a student using Google Colab or something like that, they're probably less worried about the guarantees that it was done correctly. Maybe they don't mind running it a few times. They just want experimental results. It's not going to be a kind of business critical result that they're using. It's more to guide them. In those situations, they're willing to pay much less for verification than somebody who's saying, I'm going to train this and then deploy it directly in my app with 1 million users. That person probably wants a lot more guarantees. So you can hand some of it to the user, but ultimately our view is it's taking each of those three kind of ways of solving verification and just setting the right levels so that you get the optimal efficiency between them all. And through time, those levels will change. So as cryptographic proofs get cheaper and easier to apply, maybe you can kind of upweight how much you do cryptographic proofs and downweight the kind of probabilistic checks. Ultimately, underneath all of that, though, you need reproducibility and determinism to do any kind of checking between these machine learning operations. And that is very hard to achieve right now. We've been working on that for a long time. We have our own libraries that guarantee reproducible execution of machine learning tasks. And we think that's going to be a very big thing for the world when we open source that technology. Because right now, you just most of the time you can't know that the task has actually been done in the same way because there's stochasticity everywhere in machine learning execution for good reason. But maybe we don't need to go too deep into that right now.
Yeah, I think what you mentioned is makes a lot of sense. There's kind of a lot of milestones, I guess, to get to a real test net or mainnet. Anything to share in terms of like timelines that you're looking for? What needs to happen before then? When can kind of people sort of expect to see this product really hit the market?
Yeah, good question. We don't like to commit to anything in terms of timelines externally. Our main goal is building technology, so we focus on the primitives underneath what we do, and I've touched on some of them there. Others are around kind of just communication between the chain, consensus, data availability, things like that. And we have solutions for all of these primitives. There's about 7 that we mainly focus on. So our goal is to progress those primitives, and when we get to the stage that a core set of those primitives are ready for consumption by the outside world, then we'll have a test net and we'll start testing with people. But we focus on information gain within the team as the main metric. So if we're gaining information fastest by just working kind of ourselves as a research team and an engineering team to build these things out, then we'll just continue doing that. At some point, the information gain of getting other people to run stuff, give us feedback, test it on their infrastructure, at some point that will be higher. And at that point, we'd love to test with people. What we generally say to the market is just come and talk to us if you're interested in testing any portion of this. We don't make a fanfare, we don't announce partnerships or anything like that, but we will happily work with people. So if you are working on a kind of core piece of the problems that I've mentioned, just come and talk to us. Chances are we'll just give you something to run relatively soon and you can run it. We just don't get too public about it because we're heads down kind of building and working on this technology essentially. The other big thing I would say is we are actively hiring right now. We have open roles across machine learning and distributed systems. So if anyone is particularly interested on working on this tech, just come and talk to us from that perspective as well. We're very keen to hire the kind of best and brightest to come and join us and work on this stuff. We hire from North America to Central Europe, fully remote, kind of all the benefits you'd expect. And yeah, keen to speak to people who are very interested in this topic. The crypto AI intersection is small, but we've been thinking about it for longer than most. So we're a pretty good place to be, in my opinion.
Love the shout out. I guess just for people who are listening and thinking of joining Jensen, it's kind of one of the projects in the space that has received a lot of attention. Fundraise, was it 45 mil? 45 mil, the last round.
43 mil, the
43
Series
mil,
A,
okay,
yeah.
sorry. Yeah, led by A16Z in the last round. Cool. I think the last thing that I was hoping to really touch upon, which I thought was pretty interesting, was and I hadn't heard this angle before, was kind of models talking to each other, what you mentioned with regard to our kind of the next stage after RLHF. Kind of wondering what kind of time frame are we talking about? What are the use cases that you think could be really interesting there?
Yeah, the timeframe's a really good question. I think it's going to progress initially through the agent infrastructure that you hear a lot of people talking about. So the idea that machine learning models basically solve the principal agent problem. They're a way for us to increase our impact on the world as individuals without having to try and align another human, which is really difficult and essentially impossible because they have their own kind of incentives. If you think about a machine learning agent, you create the incentives for that agent. So it is theoretically, if you've done it right, perfectly aligned with you, which means you have this suddenly immediately scalable way of interacting with more and more and more of the world. That's really exciting, but it's going to be a relatively long road to get there, I think, in full kind of or to the way that we think it will ultimately happen. But there's a lot of people right now building the seeds of that. So they're building AI agents that act on our behalf through the existing mechanisms of the world. So you think, hey, there's an agent that runs on my machine. It records my screen all of the time. And then I can ask it questions. I can ask it to do something. Maybe it has access to a sandbox browser or something. That's kind of the initial sort of like AI agent world. The way we see that progressing is actually it'll start as agents, but it'll get more and more and more embedded into the way we interact with technology to the point where we're actually replacing our interactions with data structures and technology itself instead of being this imperative kind of I tell the computer exactly what to do, it moves to this like declarative, intense kind of way of working where I just tell the computer my intentions, I tell it the outcomes that I want, and it can act on my behalf. It's very probabilistic, so there'll be a kind of social shift where
Mhm.
humanity has to get used to, hey, a machine used to do exactly what I told it, and now it does its own thing, but it still achieves the goal I wanted. So actually, it's okay. A little bit like we saw with self-driving cars, where you look at the safety standards of self-driving cars, and they're actually better than human drivers. But we have this sort of mental block where we think, I don't know exactly how it's going to deal with this obstacle, so I'm uncomfortable. But long term, it's achieving the goal better than I would. So actually, it's probably better. Same thing will happen for all technology. At the end state, or not end state, but the kind of vision that Jensen has is we seamlessly interact with machine learning models themselves. So instead of us kind of updating records in a database when we use the internet, we're doing tiny model updates. We're just giving it new information and new data, and that model is shifting slightly to represent that new information. And the whole human knowledge base that exists as the internet is then an enormous embedding space full of shards of models that you and I are just constantly interacting with, constantly tweaking, but in that probabilistic way. So it goes from agents to a new way of interacting with a shared knowledge base of humanity via agents and via models, because we can't update those embedding spaces ourselves. Whereas before, maybe I could go into a database and I could change a record. That doesn't exist anymore. I have to do it via models. So those models have to have access to resources, and they have to be able to act on my behalf in all digital scenarios.
Yeah, it's definitely building on a lot of the initial work that the industry is working on, whether it's AI agent infra or intent-centric protocols. So yeah, kind of looking forward to that long-term vision. I know we're at about time, Ben, but is there anything that you kind of want to let the audience know that we've kind of missed out so far?
Probably one big thing, which is a lot of what we talked about here is quite long term, and I think we as an industry, the crypto industry specifically, can think quite short term. But there's a lot of really interesting things we can unlock in 5 years, 10 years, 15 years time if we build things right now. And Jensen's goal is to build things right, and we'd like to make sure that people have that focus because we think that's how you build real kind of new, exciting things for the world. Is if you focus on getting the primitives correct rather than kind of rushing something to market in order to capture kind of user interest and demand. That's interesting, but it doesn't solve the big problems. It does that sort of 10, 20% improvement on what we had before. Jensen's interested in orders of magnitude change. So if you're also interested in that, like I said before, we're hiring aggressively at the moment. We'd love to talk to people who are interested. And just a reminder to the rest of the kind of industry that that's the way we work, and it's the way we kind of would like to see other people work. And there's a lot of stuff to do to make our vision exist. We're very happy to talk to anyone who's doing adjacent pieces and wants to kind of work together, get our thoughts, maybe test stuff together. We're super open to that. But yeah, the long term kind of vision is our goal.
Cool. Awesome. Well, thanks so much, Ben. It was a pleasure as always. And thanks everyone for listening.
Likewise, thank you.